Okay, so what I'm going to tell you today is basically we have how to implement this network transportation. More or less, I already have the main ideas in place since we were about how to do the unfoldings last time, which is kind of like the biggest thing. And after I kind of like tell you how to do them, I'll say a couple of things about how they're supposed to work. Let me do an example depending on how much time we have left. If not, I'll kind of like do some more of the stuff on Tuesday. But yeah, before I show you how it's supposed to go, let me just remind you something about the SVD decomposition, which I'm not sure if I have said it last time, but it's, in any case, it's useful to remember right now. So the SVD for a matrix, the way I had written it in class, it was U sigma V transpose, right? Or this was M by N, this is M by M. The matrix sigma was M by N, and V transpose would be N by N, right? And that's usually like the SVD decomposition. There's an equivalent way of writing it, which is called the truncated SVD. Okay. Which you can kind of like understand if you write a matrix in terms of like the the tensor products, because basically what the SVD gives you, right? We have talked about this before. It gives you like a decomposition of the matrix as a sum of tensor products, right? So in the sum, basically what you notice is that you don't really need all the eigenvectors, right? Like the vectors, just to remind you one more time, how the matrices U and V are constructed, right? Like you find the eigenvectors for this matrix A transpose or and transpose A, depending on what you want to do. And then the matrices U and V, they are the matrices whose column vectors are the eigenvectors of those matrices, right? So they are matrices of eigenvectors. Um, but if you notice, like the tensor product decomposition, what it tells you is that of the eigenvectors, the ones that only really matter are the ones, that are associated to the non-zero singular values, right? And so the truncated version basically just does that. Like it just keeps those eigenvectors that are um, related to the non-singular values. I will write it in a way that's a little bit more convenient for what I'm going to do next with the tensor decomposition. So I will, so this is not something that you usually do with the truncated version, but I'll just imagine that you reabsorb the coefficient of the singular value into the second vector, just because I will find that convenient for the tensor trains. So I will. So basically, I just move the scalar values into the second vectors, and so that it looks a little bit more clean. And then you can think of this as a you can write it as a product of two matrices, which I'll call both of them kind of like U tilde V tilde, um, or UT for well, I mean, I will. Do I want to? Let's use U prime V prime. Okay, like. So basically, the idea here is that it is, let's call R the rank of the matrix. So this matrix U is the same matrix as before, but it only has like the first R columns of the matrix. So this is kind of like an M by R matrix, and this is going to be an R by N matrix. Okay. Or like the matrix C just keeps the first R eigenvectors, and the matrix C keeps a the R grows with this like rescale wood. Okay, so it's kind of like that's why it's called truncated because it's literally just like a fractal, like a portion of the original matrices. So it has like the first R eigenvectors, and these are like the first column. Well, these were column eigenvectors, right? Column. Well, and when I say eigenvectors here, I mean like modified by this element that you absorb into the second one. So that's how I will think about the SVD. The advantage of doing it that way is that then like the matrices that appear in the factorization, if you think of this as some sort of matrix factorization, that they're not as big because the number of columns or rows like is given by the rank, right? So they just are like smaller matrices to work with. Oh, if the rank is small, or if you translate it, right? Because we have talked about this before, like if you that's also why like I asked you to do this experiment with the faceless and the images. If you look at the item the singular values, sometimes they come up pretty quickly. So even if doing like a truncated version as well, where you just keep the first 10 largest singular values or whatever, that is a possibility. So by writing it in this way, it's kind of like understood that you're trying to kind of like compress and getting that stuff. So far, so good. Is that making sense? Okay, now let's have fun with the tensor. So I'll show you the tensor training for tensor order form because once you kind of like see how it works with order form, you kind of like believe that it's kind of like the same idea. It's kind of like a recursive algorithm, right? So once you actually understand the first step, you're done. But like it's kind of good to see it kind of like at least play out in fully. And so if you do it with tensor order form, it's kind of like easy to kind of like write everything up without like being too time consuming. So I'll do the tensor train decomposition. And then I'll say kind of like some general remarks and what have you. Again, if you call them tensor trains, then it's kind of like and as I mentioned before, like they also go under the name matrix product states, and I'll remind you again why you usually call them that once we do some like examples. Also known as matrix product states. The terminology, the second one is more common in physics. Or I think that's where we are actually. But okay, so let me show you. Let's do it for a tensor of order 4. So I'll call my tensor T, and again, it will have 4 legs. The legs will be I'll in this case I will kind of like to keep track of things better. I will kind of like show the name of the leg, that which index it represents. And I'll use a color also to make it easier. IJKL. Okay. So the first index, let's say, takes N1 values. So the number of values for the first index is going to be 1. The number of values for the second index is going to be N2. Sorry, not 1, N1. The number of values for the third index is going to be N3. And the number of values that the fourth index could take is going to be N4. So as a hyperbox, right, hyperdimensional box, it could be presented geometrically, right? This has N1 times N2 times N3 times N4, right? So it has Okay. So step one is that I will do the mode one unfolding. So what does that mean? Let me write it down. Again, the unfolding just means that you regard the tensor as a matrix, right? And so the idea is that if it's along the first mode, um, um, then that means that you keep I, the first index is being called I in this case, right? So you're going to think of this as kind of like a matrix. Since I'm going to think about it as a matrix, I'll call it A, just to kind of like compare it to the singular value decomposition, right? So, so the first leg is kind of like just I, and the second leg, right, it represents kind of like the image of J and L in some relabeling, right? Like there's this relabeling that you do so that you know. So, okay, but the idea is that, like, just to kind of write it, sometimes it's called like multi-index notation, or kind of like alpha. I'm calling it alpha, but it represents kind of like JKF, right? Like it's kind of like sweeping through those values of JK and L. So I still takes like, the I still takes N1 values, right? And the other one takes N2 times N3 times N4 values, right? Okay, just apply SPD to A. That's it. Like, if you write it again, if so next step, step two, apply SVD. Okay, so again, what does that truncated SVD, like, truncated SVD. So that means that A is going to be this matrix, which I call U prime, V prime. Well, I guess since, I mean, it's going to be a bit nuisance, but like, I don't want to introduce too much expectation, but like, this kind of like the third matrix we're going to produce, we're just call it A1. Um, okay. And so again, what's the size for the matrix? What is the size for the matrix A1? A1 was an N1 times N2, N3, N4 matrix, right? So U1 would be N1 times R1, where R1 is the rank of the matrix A1, right? So N1 times R1. And that's what U1 would be. And the other one would be R1 times N2, N3, N4, right? Okay. And like again, if you wanted to do it as a diagram, then you have A1, and then you had I, and then you had this multi-index alpha. And what the SVD tells you is that that's the same as this matrix U1, right? For the matrix U1, it's kind of like the same, like the first index is kind of like 2, 6, and 1. So it's like kind of like the first index is the first leg is I, that's what I meant. So, and then this being contracted with the second leg, right, with this other matrix V1, right? And this matrix V1, it's like the one that would kind of like corresponds here to alpha. Well, I mean, should still keep bringing the primes, I suppose. Okay, in that we will keep U1 as it is, and then we will modify V1. So you see where like it starts being shrunk, the process. Okay, so we will preserve, so we will keep, and then I'll do maybe some relabelings later so that it matches like how people usually refer to these things. But for now, let's just leave it like that. So I'll keep U1 prime, and then I will modify, I kind of like, I have to turn this back into a tensor, and then like we apply the same procedure. That's kind of like the game. So you take the tensor, then turn it into a matrix to the LPD, in the second, then you turn the second factor into a tensor again, then you matricize it again in a different way. It's kind of like a back and forth between producing a tensor and a matrix, basically. And then modify V1 prime. So how do you modify V1 prime? Okay, again, so let's call this step 3. So again, this was step 1, this was step 2, step 1. Now we have step 3. If you look at V1 prime, right? What matrix was this? It was R1 times N2, N3, N4 matrix. Okay, so I will regard it, okay, I will tensorize it. I will think of this as a tensor. Turn it R1 times N2 times N3, N4 times. And so it's kind of like to kind of like isolate that and come back. And then I will, okay, so now I have this tensor and I'm trying to kind of like apply the same process to this tensor. So what I'll do is turn it now into a matrix, but the matrix will be R1 and 2 times and 3 and 4. It's kind of like a fun game, which then gets turned into an R1 and 2 times N3 and 4 matrix. Okay. So I'll call this matrix A2, which I'm going to apply the SVD again. So A2 again is an R1 and 2 times N3 and 4 matrix. That's what the matrix is. Okay. Then when we do the truncated SVD, what happens when we do the truncated SVD? This gives you U2 prime times V2 prime, or U2, again, what is the size of V2? that would be R1 and 2 times R2, right? Where R2 is now the rank of this matrix into right, and the P prime would be R2 times N3 and 4. Okay, so again, if you want to do kind of like a diagram, like what you had is A2, you had two legs, right? And that what they're saying is it the same as U2 prime, or there's this leg here, and there's this matrix V2 prime, where this is this other leg, and yeah, so it's being contracted as always as long as that's right, but one that's being contracted into. So kind of like in a sense, like you should think of each of these as kind of like being a multi-index because it represents kind of like R1 and 2 and and 3 and 4. So like just kind of like to keep track, you know, this one, so this one is related to R2, and this one is kind of like almost like a multi-index. So this is related to R1 and 2, and this one is related to N3 and 4. Okay. So what I'm going to do is kind of like take, we'll keep U2 prime, but I kind of like will split back the multi-index into like two regular two. So I will turn this, I will convert this one into a tensor with three indices. So kind of like the next step, again, uh, you convert U2 prime into a order 3 tensor, which is of size, you know, R1 times N2 times R2. Okay. So, okay, so like so far, what I have is kind of like, what do I have so far? So far, I have let's start putting all of it together. So far, I had this matrix U1 prime. One of this index, just to use the same colors. This index was I, right? And the other index for And the other index for this matrix U1 prime was related to the rank of the SVD decomposition. You know, this one was related to the rank, related to R1. Right, it was related to the rank of the and so, and then when you turn it into a tensor, of order 3, I'll kind of we'll call it the same because otherwise it would be too much notation that I have to introduce. So one of the legs is related to R1. Right, so this one is related to R1. The second leg is related to N2, so that is the leg for J, right? J had N to N. So let's go back to J. What color I use for J? I use blue. So this one what would be related to J? I mean, of course, you can check. I mean, the idea, I mean, there is some new annoying things checking, like, the mode when you hold and refold, when you turn into matrix and tensor, you kind of like all works out and you can just kind of, keep track of things this way. But it's kind of logical that you should have it that way. So it's just kind of like a bit, right, kind of boring to do it. It's kind of like just easier to kind of like think about what the, and then the third leg for this tensor, would be related to R2. And then we're almost there first. Then you go back. Okay. So again, you always kind of keep the U's and then you kind of like reshape the V's. That's kind of like the idea. Okay, so the next step, okay, you look at V2 prime. So you work with V2 prime. This was a matrix. Again, one of the legs was related to R2. And the other matrix was related to N3 and 4, right? Oh, okay, so. So kind of what before, basically, if you want to think about it this way, you first reshape it into a tensor with 3 legs, which, okay, so reshape it into an R2 times N3 times N4 tensor. So it's going to be a tensor with 3 legs. And now you merge the first two into domain. And then it's unfolded into an R2 times N3. Sorry, R2 and 3 times N4 matrix. And then into an R2 and 3 times N4 matrix, which I'll just call A3. And that's the last one we will have to apply again. So this is always kind of like moving around the rack. It's kind of like it's kind of like opening, closing, the left. Kind of like merge legs, unmerge, merge, unmerge, and things like that. It's kind of like a fun. It's mostly like a fun game with like the indices, that you are doing here. And so A3 again, A3. If you apply the SVD to A3, it would be again. This was R2 and 3 times N4. And so this would give you what? It gives you U3 prime times V3 prime. And then this one is R2, sorry, it's R2 and 3 times R4, right? Where R4 would be the rank for this fourth decomposition. And the other one would be of rank R4, oh, sorry, of size R4 times M4. Okay. Oh, oh, yeah, yeah, sorry. Yeah, it's only three, yes. It's next four, but you one, two more LBD, yeah, yeah. So I need to talk that, yeah. I was like, when did I do the four? I was thinking, when did I do three? Like, yeah, it was only, yeah, 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 good, good. Yeah, yeah. Wait, oh, in fact, okay, this is entry. This is what messed me up because I wrote R3 here and then that's why I confused. Yeah, it's R2 and 3. Okay, thanks. R2 and 3 times M4. Oh my God. Times R3. Oh, yeah, yeah. No, no, it all makes sense. Okay. Whew. And then again, you kind of want to keep you three prime as it is, but first turn it back into a tensor. So you kind of like break apart in slacks. So you turn U three prime into an order into a R2 times N3 times R3 tensor. Which again, I'll just call the same because otherwise, like you have to introduce so many new letters. So just by saying the size, it's kind of understood. Like the way I'm expressing the size will tell you whether I'm thinking of it as a tensor or as a matrix, and also like the number of legs that I'm drawing for it. So if you do that, what is the color that I was using for J? For J, I was using sorry, for K, I was using green. So K was related to N3. So this would be K, and the other two legs, one leg is related to R2, and the other leg is associated to R3. And in this case, like basically, if you look at B3 prime, like there, like you kind of more or less already terminate because if this had been like a product or something else, then you can like kind of like keep doing the same game, right? But here you can terminate it at B prime, B3 prime. So B3 prime, if you look at it, one of its legs, you know, one of its legs was related would be like the one related to L, right? So that because that's with N4, so this one of these legs would be L for the index L, and the other one would be like the ones that related to R3. So when you put them all together, basically if you kind of like keep track of everything, like the unfoldings work so that you just end up having the tensor T. I'll just copy paste it here. So the tensor T in this decomposition, it looks like this. It looks where so this one was what I was calling U1 prime, this one was what I was calling U2 prime, this one would be U3 prime, and the last one is kind of like this prime. It's just like you kind of like give them like, and then these legs where the sums are being, where the subtractions are taking place, those are called like the virtual legs or virtual indices, because the idea is that they're kind of like dumb variables because they're being added over. So, but again, this one is, the idea is that this one is related to R1. This one is related to R2, right? Like, so that, like this leg, the values it takes is up to the rank one of the entity composition. So the entity composition is not like determining how big the virtual legs are. And so these are called, yeah, like these are called virtual legs. Like the legs are being contracted. Contracted are called the virtual bonds or virtual legs. I mean, virtual bonds is usually the more common notation in physics. Are called. The idea being that it's not like again, it's kind of like not one of the original indices. So it's kind of like not a fake one, but it's kind of like and a two, but it's used, but it's not kind of like being out there. So yeah.
So since you have this virtual indices like R1, R2, you can ignore the B and little because based on the R1, you can see the beta or the limit except for the last one.
Well, I mean, it's not that the V's like the V's were always being used because they became the next matrix to which you would apply the V, right? So the V's are the only one that kind of like survives as is the last one, right? But I mean, but right, the common notation, but they're kind of like all on the same footing, there's something, because one is kind of like it's always like an SPT of the previous one, right? Like that's kind of like you're finding them. So the way in which this is typically written is that you call the disks or like the tensors like in the tensor train decomposition course, and then you just call like you just call them G1, G2, G3, G4 to kind of like not kind of like suggest that they have like kind of like a different nature, so that it kind of like looks more like unequal standing. So but yeah, like the way we're building them, you know, so this is like the more common notation. And then G1, G2, G3 are called the cores of the tensor train decomposition. But yeah, I wouldn't say like that you ignore the V's. It's just that you didn't keep the V's as they were. You kind of like had to, apply the then again. G's. But yeah. G1, yeah, I know. Yeah, I don't know why the word letter G goes there, like why they chose G's. But yeah, it's G1. Let me see. G1, G2, G3, G4. But I mean, if you kind of like, I just wanted to really work it out all like for one example, but you can imagine how it goes with plan. Like, if you have more ages, this continues and be long. But it's not like, it really just like a cycle. Once you understand one full cycle, once you understand how do you get to a tensor with one fewer lag, let's see the process will turn, right? Uh, but as I was saying, like kind of like the cool thing here, is that like just think about it from like a numerical data science perspective, where you will be okay to store this thing. I need n1 times n2 times n3 times n4 numbers, right? So just like as a storage capacity concern, you need n1 times n2 times n3 times n4 versus, right? If you do it the other way, right? This one needs n1 times r1. plus you would need the numbers like, okay, so this tensor has 3 legs, so it would be R1 times N2 times R2. This other order 3 tensor would be R2 times N3 times R3. R3, and this other one, being R3 times N4, right? R3 times N4. So for example, like it's sometimes easier to understand this in the case where like like if all of these numbers were less than n, right? The most that this would be is kind of like n to the 4, like kind of like in the cubical case where everyone has like the same number of entries, right? So this would be kind of like n to the 4. It's kind of like an n to the 4 versus, okay? And then if you knew that the ranks are always below a certain bound D, or you just truncate them, right? Because you do truncation and you just keep certain singular values every time you were doing it. So if you then it would not be exact, right? It would be an approximation, but like most of the time there would be some approximation involved. So if you truncate the ranks by, if you say that all the ranks are less or equal to D, some number D, then this would be like, the most it would be kind of like quadratic in D and linear in N. So it's kind of like O of N D squared, right? Wow. So this is like, actually, I should write it like this. Like this is kind of like an O of N of 4 versus like an O of N D squared, right? So if you change something that's quantity, right? Because it has 4 legs. If you had like L legs, it's what it would be N to the L, right? So something about exponential, right? In the number of legs is something that is kind of like linear. We just got like, or maybe the number of entries, like for each value of that.
So does that mean you can change your chorus to get a smaller source capacity with the order?
Oh, right, no, like well, I mean, there are definitely the compositions that first, like the composition is not unique as you might have guessed, right? Because you have to choose one index. You have to declare, oh, this would be the first index that I apply the decomposition to. So there's this, that's what I don't want to say next, but this is not a unique decomposition by any means, right? So there definitely could be better, tensor train decompositions than others, and that's yes, and also like again, like depending on how you decompose it, maybe you decompose it, like there can be some better ways where like maybe like certain decompositions already start with low rank. And and all these different possibilities where like that's where people have to do like active, like that's where the active research is, right? Like how do you do this slightly better way than this other method, right? But it's not like a very much like broad strokes, like the big idea, the big picture. But there's actually like a fun paper that I'll send it on Canvas, but it's kind of like how to do this in parallel because this is kind of like being done in series, right? Like you have to do the next step, you have to do the previous one, but there's kind of like a way to set it up as a kind of like more like in parallel, and it's kind of like a cool idea as well. So like there's so many, and that's why you appreciate like numerical analysis because it's kind of like an art. How do you do this in a slightly better way, even if mathematically, in mathematics you have infinite resources, right? Like it's kind of like more like a godlike thing. You can do things like and you don't care about how much time it takes. Like so that you prove that it can be done. But like then down to where you actually having O and 4 minutes versus O and 3.75, that's a big thing, like, and that could be like a very big proof, like, how do you prove it by even that amount, right? So, but they're definitely, then yeah, that opens kind of like the questions of, oh, what are the better, what happens if I do the different tensor trains decompositions, like are some more advantageous than others, etc., etc. So yeah, like all those questions definitely there are things that people think about, of how to use them better. But even just like it's impressive, like like the perspective, like again, like, just to think that you're turning it, like before you kind of like go through the details, like if you thought someone, oh, you're replacing something that looks exponential, like in versus like something that looks linear, it sounds like amazing. Of course, you know, the trick is on the D's, right? So if you don't control the D's, right, like you may not get any, you know, any advantage. But the idea is that, you know, if you truncate or you do approximations, you can do like better things. But yeah, like before, let me just mention this. Like so, right? Like there's this non-uniqueness, which is very easy to understand. Like it's a very fun diagram, actually. Of the decomposition, that's what I mean. So for example, imagine taking one of the tensor trains. Imagine you had already found a tensor train decomposition. I, J, K, and L. Okay. Well, so hopefully this makes sense. Oops, like I didn't write that leg for the last one. Okay, let's see. So hopefully it makes sense. Just to show you, this is like an intermediate step. We're not, you know, it's not a tensor train per se because like, you know, it has like this thing without like any of these bullets, right? So that is no longer a tensor train. But as a tensor, that is the same tensor, right? Because you can always put the identity matrix wherever you want, right? It's not like multiplying by the identity. Never does anything. But if you kind of like, but what is the identity? The identity is basically of the appropriate size, right? You just have to think of choosing the right size for the identity matrix. But you can always express the identity matrix as a matrix M times its inverse, right? And then kind of like imagine like breaking these into two bubbles, and then you can like move one bubble, merge one bubble with the other, right? And then it's kind of like a fun trick. So this is the same. It's just like a very easy way to show how you can modify the tensor train structure, right? Like you just make an insertion of something. Uh, but that can be used to your benefit, right? Because that, you know, like maybe there are useful insertions to make. And so you kind of like the idea is that, again, you kind of like think about breaking it into these two. And right, like you kind of like, you have merge these two together and merge these together, and then there's another tensor train decomposition. So. Well, I mean, I'm being here a bit like sloppy with the notation, right? Because, you know, I mean, this one definitely is kind of like what in like there is kind of like literally in like, you know, I mean, because the matrix was this was a matrix, so and this was already a matrix to begin with. So this is really kind of like the matrix multiplication. Here it's not like a it's kind of like a matrix multiplication, but kind of like along the leg that they share, right? So it's kind of like a contraction along that leg. Um, But all that I'm saying is that that is like a very simple way to change the structure. Okay. here's a concrete example of a tensor trait decomposition. So then you see one that's you're curious. So let's like, okay, and maybe we can be done with this example. And then next time I'll tell you a few more things. So here's like an actual example, like an actual function, actual tensor. So here's a concrete example. I'll do it with like, I still working with the tensors of order 4, but that's just like, again, do not write too many things. So imagine you had this function of 4 variables. And like, let's think that this is kind of like continuous. So like like the variables are between 0 and 1. Each of the variables are between 0 and 1. Okay. So in numerical analysis, many times when you have like a function of multiple variables, you discretize, like the function, right? Because like, working sometimes with. So you kind of like discretize the interval 0, 1. So meaning that you choose like a number n, an integer n, which is large enough, and just imagine like, breaking it into n intervals, and you choose like a value from each of the intervals, right? So you break it for n large, like, for this to maybe be realistic. For n large, then we like break this into the interval from 0 to 1 over n, from 1 over n to 2 over n, right? From 2 over n to 3 over n, and the last step would be for what? From n minus 1 over n to n over n, which the last one obviously being 1, right? And then it is also the second 3 months off. And then we just break the interval into smaller pieces. And then, like, just to make my life easier, I just imagine that now I force I'll just force and like I'll force x1, x2, x3, or x4 to just take the values of the left hand one. Okay, so I will discretize the variables x1, x2, x3, x4 by just asking them to be so discrete and just like n equal to one of the left endpoints of these intervals. So then this kind of like a vector is split, like now, so, one of these variables is, so any of these variables takes values of the form, like, just call this, n over n, where n is equal to 0, 1, 2, 3, So xi equals n over n, where n little n goes from 0 up to n minus 1, and the i's are either, 1, 2, 3, and 4, right? Just like that. So the infinite tensor, okay, if you think about, I'll define a tensor of order 4. T-I-J-K-L. Which is just going to be, the sign, I mean, I will write it explicitly if you want, I'm thinking about like the sign of I over N plus J over N plus K over N plus L over N, where again, like I, J, K, L are just, go from 0 to N minus 1. So this is kind of like an X, like the different version of X1, this is 3X2, right? So this is kind of like my discrete X1, my discrete X2, my discrete X3, my discrete X4. It's a bit easier to think about it that way. Okay. Now this is actually a good maybe moment to mention this. We can think of it as like the other time. Why is this called like sometimes a matrix product operator? Why is this a composition of matrix product operator? Or called that? Because if you think about giving particular values to I, J, K, and L, if you fix the values for these, like 1, 1, 1, 1, or whatever, then these are not being summed over, right? Like the only ones that are always being summed over are the virtual indices. So you're only taking the sum over two legs at a time, which are matrix multiplications, right? So except for the last and the first one, the kind of like the things in between is always kind of like a matrix product. So what that means is that you should actually see matrices here if you were to express it out concretely. So, actually, it's kind of like I'll put it as an exercise so that you can check it out. It uses some complex numbers like Euler's formula, but it's kind of like a fun exercise to check that sine of x1 plus x2 plus x3 plus x4. Again, which I'm thinking of being like the entry of TG, TI, JKL, right? Like in this discretized version. That is the same as it has this decomposition. Okay, I'll need to shrink this because otherwise it won't fit here. And times cosine of x4 sine of x4. Oh, isn't that cute? Yeah. Well, these are rotation matrices, right? Because if you write Euler's formula, e to the I theta is cosine of theta plus I sine of theta. You represent that as a two-by-two matrix system. Okay, but so these, okay, and this is a product of matrices except for like the first and last factors, but think about it basically, I mean, like these are also special cases of matrices, like the first and the last one. But kind of like the idea is that, okay, this really, because the axis can take like different values, it has like three legs. I mean, you should imagine like kind of like, it's 2x2, but if you include the possible values for the axis, it kind of like becomes like a box, right? So that's why it becomes like an order 3 tensor. It's like, but in directions, but there's kind of like a third direction where like they were giving like the different possible values to to the x2 or the x3. But if you fix one, like if you fix x1, x2, x3, x4, where like you're just looking kind of like at one of the pages of the boxes. And so these kind of like your G1, your G2, your G3, and your G4. You see, which is kind of like cute. And because these are 2x2, like the grounds are 2 at most, right? So it's like a decomposition with so here like the R's are always less than or equal to 2, right? Like it's like a cool one, right? Because we should compare this with what like the tensor brand is like would be, right? Like what, like when you, if you were trying to find like the tensor rank decomposition. It would have been something like, kind of like a something that, kind of like, how should I write? Let's say, something that depends only on X1, it's something that depends only on X2, it's something that depends only on X3, it's something that depends only on X4, right? And that is basically, you like for something like the sign that, like, I mean, even if you discretize it, like, it's going to be large, but in the matrix product representation or in the tensor train decomposition, it's quite small, right? So it's not like a difference of size, right? But it's like a good output, like another similar one on the X define. I'll put some of those so that you get kind of like a more like thorough vision of what's going on. So, but it's kind of like fun to see some examples of that, and if you probably actually work out. Okay, let's finish here in case like someone wants to stick around to just talk a few more things. But then I'll tell you some other useful things like here, like how do you do inner products or find lengths of norms of tensors, like from the tensor train decomposition, because those are also things to know. I'll tell you more about that before we move to applications. And after that, we can start talking about applications. But there are a few other things that are worth discussing about the tensor trains before we do applications.